We have a tremendous group of patriots that are lined up to discuss our track number one in this aspect of exploration, emerging solution to the Arctic Communication Challenge. This group, led by Arctic Slope Regional Corporation Federal Mission Solutions, are truly a tremendous group of people that are associated with the largest Alaska's Native corporation that is federally recognized. ASRC, of course, is focused. It has headquarters both in Nukjavik, Alaska, as well as here in Anchorage. And ASRC Federal Mission Solutions is out of Bordentown, New Jersey, part of the ASRC entrepreneurial enterprise. I will take a moment to introduce our distinguished array. We have Mr. Bruce Heinrich, Mr. Mike Bernardo, Mr. Orest Urgansky, Dr. Steve Kanjajar, and Mr. Steve Specht from ASRC in Lockheed Martin. I will go through their brief bios here, if I could, just bear with me, because I think it's important for you to learn a little bit about this remarkable crew. Bruce Heinrich is a program director of Maritime Warfare Systems at ASRC Federal Mission Solutions. Bruce has nearly 20 years of experience supporting leading defense programs and supported DoD efforts in DDG 1000, AMDR, LCS, Deepwater, Aegis, which is Navy vessels baseline, Ballistic Missile Defense baseline 9 and 10. Prior to joining ASRC Federal, Bruce started his professional career in software engineering, worked for both small and large commercial software companies. He was also Adjunct County College physics and chemistry teacher. Bruce earned his BS in Rutgers University and is currently pursuing a Master of Business Administration. Orest Urgansky is the Director of Innovation at ASRC Mission Software Solutions. He's over 30 years experience in nucleating novel solutions for a diverse customer set. His experience ranges from fiber optic communications, automated command and control, high-speed amphibious craft, autonomous systems, renewable energy, and more. Mr. Mike Bernardo is a solutions architect at ASRC Federal Mission Solutions in Morristown, New Jersey. And I guess for the sake of the discussion, Morristown and Bordentown, they're awful close to me, so I probably said one and meant the other, so forgive me for that. But I've been in that neck of the woods in the past, and so I kind of lumped them all within about a 5-minute drive. My memory serves me somewhat correct. Mike participates in engineering development software activities for Navy's Aegis weapon systems. He has 38 years of experience and diverse software experience on Aegis, as well as other ASRC Federal Mission Solution projects. He holds a BBA in Computer Information Science from Temple University, Master in Computer Science from Villanova University. Dr. Steve Kanjajar is a data scientist specializing in synthetic scene generation and physics-based animation for use in autonomous intelligence and machine learning studies, and in experience in both AI's training simulation and optical process synthetic scene development and avatar animation. Steve has also published over 20 papers in remote sensing, medical image processing, and RF signal recognition. Over his 30+ years in research, has been chief scientist at Lockheed Martin, I can quote in parentheses, King of Prussia, and a technology fellow for the last 10 years while I was at Lockheed. Major accomplishments include corporate-wide distinction for his work in hyperspectral scene modeling and international first place award in melanoma early warning skin cancer detection research. His most recent contribution in last year was being the inventor of an SDR-based signal detection algorithm, and there's a provisional patent underway. Steve Specht is the Chief Engineer, Army Technologies for ASRC's MSS division. He's been at ASRC Federal NetCentric for 10 years to helping to lead and design the development of software solutions for customers, primarily focused on the U.S. Army's market. Prior to NetCentric's acquisition by ASRC, he served as a Vice President for Product Development, where he's responsible for leading the development and delivery of 5 technical software applications to the U.S. Army to support intelligence and battle command functions. Before joining NetCentric, Steve worked as U.S. Army Communications Electronics Command for 7 years, serving as a Chief Software Engineer, U.S. Army Mission Command and Software Lead for the Army's Future Warrior Program. Steve is a BS in Electrical Engineering from Columbia University and a Master's in Engineering from Princeton University. Ladies and gentlemen, this is a profoundly wise and technologically advanced panel. I'd like to give the floor over to Bruce, Mike, Orest, Steve, and Steve to offer their reflections on emerging solutions to Arctic Communications Challenge. For those who don't know, Bruce is leading our efforts in ADAC from the ASRC side, they're supporting our Alaskan and Arctic Maritime Communications Connectivity Analysis, a project that is being led by the center. Includes, of course, our principal investigator, Doug Causey, our associate director, senior research professional, Mr. Jason Rowe, and a distinguished researcher from the Sandia National Laboratories, Dr. Mark Ivey. Bruce and Mike, or Steve Z, please take it away.
Hey, good morning, good afternoon, everyone. Church, thank you so much for the warm and welcoming introductions. As Church had mentioned, I'm with I'm very fortunate to be part of this team and part of this group out in bright and sunny Morristown, New Jersey, if you will, and not to rehash what the introductions that Church had provided in terms of our corporate structure. I will offer that, as part of ASRC Federal, we are fortunate enough to be part of a virtual network of over 8,000 employees and a diverse set of skills and engineering disciplines. With you this afternoon, there's a key grouping that works directly with me over here in Morristown, and we'd like to present to you some thoughts and offerings specific to how commercial application of technology could support the maritime connectivity challenge. So with that said, I'm going to hand it over to Mr. Mike Varanato, and he's going to walk us through and orchestrate this afternoon's discussion.
Yeah, good morning, good afternoon, as the case may be. Thanks for having us today. This discussion we're going to have today really represents some research we've been doing along the line of analyzing RF communications, and in particular, how we could use artificial intelligence to augment some of the the communication paradigm in an effort to meet the unique challenges of the Arctic. So I'll just kind of get into it to give you a little bit of an overview of what the basis of the research is, and I'll turn it over to Steve, who's largely responsible for the technical research. So, we understand, and we heard a little bit this morning from Church and Mr. Mean on the demands of the Arctic, increased demand of traffic, the geographic issues, the line of sight limitations at those altitudes with satellites. And then, there's unique atmospheric conditions in the Arctic, specifically causing a loss of communications, loss of signals, degradation of communications. We know there's a extreme sea state, so that causes problems with ships and maritime and line of sight to the satellite, weather impacts, of course. And then we saw a graphic earlier with the coverage of the area, sporadic coverage of RF communications in that area. All these kind of represent the challenges unique to the Arctic region. So the basis of this research really comes from software-defined radio technology, or SDR. So we can use that technology to understand and characterize the RF spectrum. There's a sampling of devices here. They go from simple, dongle devices that are, under $20 to a little more complicated receivers that allow you to receive, RF transmissions and characterize them. And then the top of the line, real expensive type models, not shown here, allow both reception and transmission for a relay capability. But the point we're trying to make here is that this technology is evolving. It's replacing traditional hardware communications gear and augmenting it with software capabilities, which is really where we can take advantage of some of this and apply some machine learning techniques to that. So typical for an SDR is a display output. So Steve will be talking a little bit more about this, but I'll just kind of ground you into what we're talking about. On the top of this box, you'll see a signal display. It provides the The signals, the peaks are signals or points of signal capture, and then the valleys would be really noise. So the trick is to figure out how to determine what is the signal versus the noise. Noise being what you would hear if there was no transmission going on over that frequency. The important part of it are these waterfall displays or ribbons that you see at the bottom. So through this technology and through software, we can extrapolate and segregate the different frequencies. You know, for example, one might be Morse code, another might be marine traffic, another might be television traffic, you know, and once we have isolated those, then they're ripe for exploration and exploitation to kind of understand what they're really telling us. So while this looks like a static picture, it's actually a dynamic picture. It's called a waterfall because as each point is measured, it drops along, and then the bottom section there is frequently moving. So I'll turn it over to Steve. This is kind of where we try to look to leverage artificial intelligence to create, you know, better communication networks through this software-defined radio technology. You with us, Steve?
Okay, everyone hear me?
Yep.
Okay, great. Yeah, this is Steve. I just want to clarify one point made earlier. I used to work at Lockheed. I put 30 years in at Lockheed. Now I've joined forces with ASRC, and they've been kind enough to let me work on their research and development program. And all the work that we're going to be talking about here is basically developed under ASRC in regards to the software-defined radio. Okay, so with that said, let's get on to this. Mike, can you go back the one chart earlier? Yes, that chart. What I'd like to maybe try to amplify a little bit about this is that this display that you see has a wealth of information that we can exploit either through AI or through image processing. And it's a dynamic two-dimensional format of information. And each of the ribbons convey not only the type of ribbon that we're dealing with. If you look at the ribbons carefully, they have certain patterns across them, and those patterns are fingerprints for the type of service that you may be dealing with or the type of modulation that you're dealing with. So you have a way of fingerprinting the particular service activity that you're trying to monitor. In addition to that, you'll see that, for example, the middle ribbon at the bottom there is modulated with spaces. You have these bright areas, and then you have these gaps. So it gives you information of the activity within a particular frequency chunk. So you can record the start time and the stop time in regions where there is inactivity in that spectral region, that radio frequency region. So you can now start quantifying the activity levels across the entire spectrum simultaneously across either the HF, the VHF, UHF, even microwave with this type of technology. Okay, so moving to this chart here, we do this really in two different steps. In one step, we do some forms of image processing of that display, and doing this image processing, we can segment the different ribbons to isolate the activity levels. We also could, in this particular process, identify start and stop time of each of the transmissions. All this can go into a large database where they could be then subsequently analyzed as to what are the active regions of the spectrum, which are not the active regions, what are regions where the communications are variable? That is to say, it might be in a fringe area where sometimes because of the environmental conditions, you have good communications, other times you don't. So you can start quantifying just how the effectiveness of communication is in that particular region. And so you can perform or identify gap regions where you can subsequently design network systems to accommodate those particular shortcomings. Once this segmentation is done, it goes through an AI system that basically tells you what types of services are actively pursuing those resources, those RF resources. Okay, the third part is, if in the future we start interfering with one another in the communication, we can have smart networks that can reallocate the frequency allocations that we're dealing with. This now is one of the examples where we actually do the segmentation. We start with our baseband waterfall display, and if you look at the waterfall display, we took a subset of that, and we see a few bright ribbons there. Those ribbons are dissected into these 4 parts. Those 4 parts are extracted in a waterfall interrogator, and ultimately this information is put through an AI system that identifies a particular type of modulation. We wrote a paper recently and reported in SPIE of an artificial intelligence system that basically takes these ribbons and performs a rapid real-time assessment of the type of modulation that is being performed. In addition to this, we also generated a patent that does the automatic activity assessment or situational awareness of the RF spectrum, that we can identify those particular frequencies that are oftentimes used, and also the amount of time or activity levels within those particular RF channels. Okay, next chart. Here is just a fairly generic AI, a CNN network that we're dealing with, a convolutional neural network that takes an input. And in this case, this is a fingerprint of a portion of the ribbon, which you see as the input on the left side. And it goes through various types of processing steps. It takes this 2-dimensional picture, which is stacked because you get multiple regions of the interrogation over time. So each one of these planes is a different times snippet of that signal. That then is processed and compressed into a smaller data domain that then can be analyzed and made into an assessment of different classes of modulation types. And in this case, it was a 9-element system to differentiate between different types of HF modulation schemes. Even though this was used for HF high frequency case, it can equally be used for other frequency bands such as VHF, UHF, microwave, so on and so forth. So we had very good, robust operation with this system, achieving 95% classification capabilities with this. So we're happy with that. We looked at a couple different types of CNNs, and we had performed similar types of robustness with the different neural net classifiers. Next chart. Now, let's suppose, and this is a very restrictive use case that we're looking at, the gap analysis case, where communications may not always be present. So by using the information that is supplied through, let's say, an array of SDRs that may be planted across the shoreline or on buoys, this can then fuel information, valuable information, as to where you may be able to augment, let's say, operational networks, relay networks. If we have a current operational antenna on the right over here supporting these 3 boats on your right-hand side, but it doesn't necessarily support the 4th boat on the left side because of communication gaps, this type of SDR mapping of the integrity of the RF space can be used to support where we should introduce other relay stations to support that particular traffic. But this is one use case. With Governor Treadwell mentioned, there are various types of paradigms that we could be looking at that where the software-defined radios can play maybe an important role. He mentioned the domain awareness innovations, where he talked about the sea, space, climate. There was a very complex network of information nodes that he showed on one of his charts. There's no reason why SDR can't play a role in identifying communication lacks within that particular network that might be able to augment and improve the networking of such systems. With that, then, I think we can go to next chart. And what we've basically showed is that we can have very cheap types of devices, these SDRs. These toggle devices are about $24 each. and they span 10 megahertz spans. So they're a very effective way of looking at broad areas of the spectrum, and you can place them in tandem to get whatever bandwidth you want, anywhere from long wave up to about 2 gigahertz. And that's a tremendous way of getting instantaneous information. It could go onto buffer systems, and it could be retrieved later to do the analysis for assessing activity levels. And I think for the long term, if we get to that stage where we have so much RF traffic up in the north where you may have interference, we can then also use AI to augment these systems, what is known as a cognitive radio, where it senses the traffic and it helps organize what station basically transmits on that particular frequency to minimize cross interference. So that's our vision at this time, but the technology is highly flexible and it could be used in multiple types of applications.
So I'm not sure if I can see the questions, if we're open to any questions.
I have a couple questions that are in that I have seen in text to me, but we'll see if there's the chat, of course, is open for folks that are welcome to text to text questions as you would like to. Strategically, I have one question. As you look to the commercial applications of this presentation, are there gaps in your understandings of technology that would make SDR less viable as a potential solution set? My apologies.
Gaps in our
yes.
Understanding of it.
Is there any gaps in your understandings at this point, sir?
Well, one of the potential areas that we have not addressed is packaging this type of technology into a closed package. Right now, we're looking at the Raspberry Pi in conjunction with the RTL SDR device. And we're talking about a device that's less than $100, but it has to be packaged so that it is compatible with the environmental swings of the Arctic. But we have not looked at that particular question.
Okay. Well, that'd be, I guess that would be when I would say potentially consider taking it for a thought to further come. I have one actually one in chat. That it sounds like the artificial intelligence aided identification was 95% correct, but how many distinct RF signals were being ID'd?
Okay.
Perhaps that detail was not covered sufficiently.
Mm-hmm. That's a good question. We looked into the HF domain that have very distinctive types of modulations that don't necessarily correspond to those in VHF and UHF, which are oftentimes used in the maritime operations. We basically took many different types of digital communication modes, specifically 9 in our case. We can extend that number, but for demonstration purposes, we use 9 that were very common in the ham domain region of the spectrum. We were, like I said, we were able to get 95% correct identification with such devices. Now, let me preface that. We used moderate to high signal to noise ratios in order to achieve that. We did not go down to SNR values of 1 or less in order to see how robust the system is. So that would be another area of research that can be extended to gain better insight. One way of doing this, of course, is by taking more longer ribbons, and the longer ribbons will give us a greater correlation gain to improve those particular results. But if we're dealing with short communications, that's not there's a trade between short communication and our robustness. We were using something on the order of 5-second durations in order to achieve the kind of estimates that were reported here today. Those estimates, by the way, is reported in an SPIE paper that we published last year in May. And anyone interested in reading more about that, they can do so.
Tremendous. Is there a way we can get a copy or a link to that? We can post it to the CIS website or the CIS URL for us here at ADAC?
Mike, did you do that?
No, but I'd be happy to send that along.
Great. I appreciate that. So I have another question here, and that I offer to you all, and that's regarding as you look to the work that you're doing here, have you thought about trying to establish a test bed and proving ground to build out this construct?
Oh, I thought about it, but I want to sit down with people to better understand the problem sets that you guys are experiencing. I'm not fluent in that environment, and once if we can sit down and talk about that, I'm sure we could hammer out something.
That's outstanding reflection. Thank you. It totally makes sense to me that something like this you have to approach carefully. But I know that, for example, our friends at the National Weather Service here in Alaska do a Arctic test bed and proving ground for technology to go into the National Weather Service evaluates. So this construct to me is I'm quite familiar with the construct. And again, applying it to the comms challenge, I think may be quite profound. I do have one of the questions come in, if I could, is that have you had much opportunity to interact with local mariners on some of the solutions that you consider to address Arctic communications?
No, not me personally.
Right. Anybody else on the team?
Not that I'm aware of.
Some of us have had communications in this area with the Coast Guard when they're trying to establish new comms for their polar breakers up in the northern region and some other areas, but not the commercial vessels yet in the area. Mostly Coast Guard and the DoD.
Right. Okay. Well, thank you. And that's a great lead-in question. There are people that are starting to tune into our new Alaskan and Arctic maritime communication connectivity analysis. And this project is one of the principles of it is to really engage with through a 5-sector regional community approach of getting what mariners are using right now in the context of their operational kit, that local mariners. So just trying to get a full sense of what their mission needs are in this regards and how communication challenges are specifically in the aspect of emergency communications that the Coast Guard supports reactions to. So again, this opportunity looking towards the future, again, as a community professionals trying to really pull that link forward or that thread forward and understanding the communication challenges at the granular level. One other question, and then I know we're getting tight on time here, but to you all, as you look to the future in communications and the number of polar orbiting comm satellites that are starting to come on the horizon, do you see this, the work that you're doing as being able to leverage new investments in commercial satellites?
I have not been thinking in that domain. I know that it was mentioned earlier that Iridium was working on low Earth orbiting satellites to augment the communication networks. I have not worked in that particular domain myself.
Great.
One of the things you can, but one of the things you can look at with the merger now of surface comms and sat comms is the fact that you can start creating comms networks, comm meshes in the area, so you can act as independent relays to broaden the reach of your comms channel where you are not able to do that before. So you can see over time where one node can receive a SATCOM link and retransmit that over to a ship that does not have the satellite comms, thereby enabling comms to that ship that it would not normally have. And you can start doing that by creating these comm networks over these radios.
Let me amplify that a little bit. We have also been working on GIS systems for modeling three-dimensional topographies and overlaying other information grids on it, such as RF communication grids. And this I think, may help in looking at heterogeneous communication protocols. So that's just something else that you might be interested in. It's a GIS type system that's based on a blender topography, and And we have three-dimensional database worldwide down to about 20 meter resolution that can then support other frames of information such as RF communication networks. So you can do what if type scenarios if you were trying to connect one point to another and identify shortfalls. We can interface this with Python analyses. There's a Python engine that's with it. We can do Monte Carlos to see the robustness of networks.
Outstanding. Then I'm familiar from my past life of mesh networks for communications and different AORs in the planet. So that approach to me makes lots of sense here to apply that same sort of logical thought to ARCTIC communications challenges. So I thank you for that. Ladies and gentlemen, let me see if there's any other questions. Let me check text real quick. That tends to be where they come in. Okay, so hang on a second, just in. Strategically looking to the future, as you see, as this team looks at communications challenges, what sort of input are you looking from the community of operators can help you better identify solutions? So what sort of input from operators would you like to see to help you advance technology to address ARCTIC communications?
Okay. Well, first, the natural environment of how they would like to have their comms optimized.
Mm-hmm.
Right. Yeah, that's the first thing. How do they use their comms? And then what is the actual end goal? Like the mesh network induces delay. Do they mind a slight delay in their comms for certain things? Also, it's just the daily operational care and feeding of the equipment that's in some of the harshest environments on the planet. Right? They have firsthand experience in how to do that. Any kind of foreknowledge of that can help us provide the right equipment at the right time for them.
That's outstanding reflection, Norris. Thank you for that. Let me, at this point, I'm watching the clock get away from me, so I apologize for that. Let me first of all see if there's anything else out there. Of course, the moment I say that, no one else is going to ask more questions. Let me give you all for Bruce and team here, please allow me to lead you all and lead the rest of the community in a virtual round of applause for your reflections. I thank you for that. And let me offer the floor back to for any closing remarks to you all as we bring the conversation back to our overall program coordinator, Ms. Matthews. Any last remarks?
No, Church, this is Bruce here. On behalf of our team, we appreciate the opportunity to offer some thoughts and exploration of some technologies that could be applicable to this problem space. Happy to entertain any conversations post this. Our contact information is posted, and thank you again.